Have a look at question 4 from the team selection test. And the question said that we had two primes, P and Q, and the idea was that P plus Q had to equal a square number, so let's call it C squared, and P plus 4Q also had to be a square number, so let's call it D squared. And the word that they used actually, instead of just square number, is perfect square. And that's because in a sense, every positive number is really a square. So it's like, oh, if you take 12, well, it's the square of the square root of 12, right? Like if you just find the square root of 12. But perfect square implies it's a square of an integer. It's a square of an integer. But we said there was both squares of integers. Okay, and then what we want to do is basically have a look at this and try and find something interesting. Now, whenever you see two squares, one thing to do is to find the difference of two squares, because the difference of two squares always factorizes out nicely. So let's subtract d squared. Well, d squared is obviously going to be bigger than c squared in a sense, because this has 4q's and this only has 1. So let's subtract the two of them. So let's take equation 2 and subtract equation 1 from it. So I'm going to get that 3q is going to equal d squared minus c squared. And this nicely factorizes out into d minus c and d plus c. Right? So now we know that d is bigger than c. Right? We know that d is bigger than c, and the reason is because this square is obviously larger than the square because there's an extra 3q's there. And so then we can actually say that d plus c must also be bigger than d minus c. Right? And so that means that given that q is a prime number, right, it's some sort of prime number, we kind of have two options. We either have that d plus c, and like let's write it as a pair, d plus c, d minus c must either equal 3q and 1. That's one option. Or it has to equal q and 3. Now there is another option actually, which is that it equals 3 and q, but in that case we would need to have q equal to 2, because remember that d plus c is bigger than d minus c and q is just a prime. But if we do let q equal to 2, right, then what happens is that we simply get that d plus c equals 3, d plus c equals 3, and d minus c equals 2. And then we add the two of them up and we get that 2d is equal to 5. And this is actually not possible. So this thing is just not allowed. Okay. So let's look at the two other cases, because those are the ones that we care about. That's this case, these two cases. And let's call this case 1 and let's call this case 2. Okay, so in case 1, what happens is that d plus c equals 3q and d minus c equals 1. Okay, and if we do that, we can kind of solve our simultaneous equation to get that c must equal 3q minus 1 over 2. Okay, and what that means is that p plus q then is simply equal to 3q minus 1 over 2 all squared. And if we expand this out, we then get that 4p plus 4q, I'm kind of taking this 2 squared at the bottom and bringing it up, is equal to 3q minus 1 all squared, or simply 9q squared minus 6q plus 1. Okay, and then we can kind of move all the q's over to one side to say that this means that 4p is equal to 9q squared minus 10q plus 1. And we should factorize this again, because we see like a 4p and we want it to be some sort of product of two things, in the same way we saw that 3q was some product of two things. So we can factorize this, and this actually becomes 9q minus 1 times q minus 1. Interesting. Okay, and we know that q itself has to be odd. Q is odd. And the reason is because C needs to be an integer. So 3Q minus 1 needs to be even. And if 3Q minus 1 needs to be even, then 3Q needs to be odd. So Q itself does need to be odd. And we also have that 9Q minus 1 is bigger than Q minus 1. Okay? That means that you end up basically getting to it, having just one option really, and your option is that 9Q minus 1, 9Q minus 1 equals 2p, and Q minus 1 is equal to 2. The reason is because if you otherwise had that the pairs were equal to, let's say, 4p and 1, right? Or maybe you could argue it could be, let's say, p and 4. Now, the issue with having 4p and 1 is that you get that q ends up being odd because q minus 1 is 1. So that's definitely not possible. In the other case, in which case that you have p and 4, then you actually end up having that q equals 5. Q equals 5, but then 9Q minus 1 equals P. So we can plug that in. So Q is 5, so 45 minus 1 is just 44 equals P. But that's not a prime. So that's also not possible. So you end up only really getting this one. So you have to really have 9Q minus 1 equals 2P, and Q minus 1 equals 2. So then and once we solve that one, we just get Q equals 3. And then if we plug that in, we get 9Q is 27, 9Q minus 1 is 26, so 2P is 26, so then P is 13. This ends up being one of our solutions, 13 and 3. And then now we kind of have to just continue with the other solution. So I'm just going to clear the page, but remember that in our other solution, what we had was D plus C is Q and D minus C is 3. So once we clear the page, we get that D plus C is equal to Q, and D minus C is equal to 3. So again, we get that C equals Q minus 3 over 2. So we again look at this. We said that P plus Q equals C squared equals Q squared minus 6Q plus 9 over 4. So 4P plus 4Q equals Q squared minus 6Q plus 9. So 4P now equals Q squared minus 10Q plus 9. And then we again want to expand this out. So this time we just get Q minus 9 and Q minus 1. Right, so again we need Q to be odd. And the reason is because this thing here, Q minus 3 over 2, is an integer. So the only way that happens is if Q itself is odd. And so in order to have Q being odd, we would need to have Q minus 1 to equal 2P, and Q minus 9 in this case to equal 2. Again, we do know, remember, that Q minus 1 is bigger than Q minus 9. So the only other real options were 4. So like we could have had, let's say, Q minus 1 to be equal to, let's say, P, and Q minus 9 to equal 4. In this case, we would have had Q equals 13, right? And then P would have equaled 12. But that's not possible. That's because P is not an integer. So you need to really have Q minus 9 being 2. It can't be 1 either because then Q is not odd. So Q minus 9 is 2. And this just gives us Q equals 11. And then P would be equal to, because 11 minus 1 is 10. So 2P is 10. So P is 5. So we had two solutions. We had 5 and 11. And we had 13 and 3. as equal to P and Q. And these are the only possibilities. So the idea was we took our equations, we kind of simplified it and kept restricting what were the options on P and Q. And until we managed to deduce exactly what the two different options that would make sense for P and Q are that gave primes, and we found that they worked. So this was the two solutions that you were looking for. Let me know if you have any questions on how exactly this came about. Thanks.